The philosophy of artificial intelligence attempts to answer such questions as: can a machine act intelligently? Can it solve any problem that a person would solve by thinking? Are human intelligence and machine intelligence the same? Is the human brain essentially a computer? Can a machine have a mind, mental states and consciousness in the same sense humans do? Can it feel how things are? These three questions reflect the divergent interests of AI researchers, cognitive scientists and philosophers respectively. The scientific answers to these questions depend on the definition of intelligence and consciousness, and exactly which machines are under discussion. Important propositions in the philosophy of AI include Turing's polite convention. If a machine behaves as intelligently as a human being, then it is as intelligent as a human being. The Dartmouth proposal. Every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. Newell and Simon's physical symbol system hypothesis. A physical symbol system has the necessary and sufficient means of general intelligent action. Searle's strong AI hypothesis. The appropriately programmed computer with the right inputs and outputs would thereby have a mind in exactly the same sense human beings have minds. Hobbes' mechanism. Reason is nothing but reckoning. Can a machine display general intelligence? Is it possible to create a machine that can solve all the problems humans solve using their intelligence? This question defines the scope of what machines will be able to do in the future and guides the direction of AI research. It only concerns the behavior of machines and ignores the issues of interest to psychologists, cognitive scientists and philosophers. To answer this question, it does not matter whether a machine is really thinking or is just acting like it is thinking. The basic position of most AI researchers is summed up in this statement, which appeared in the proposal for the Dartmouth Conferences of 1956. Every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. Arguments against the basic premise must show that building a working AI system is impossible, because there is some practical limit to the abilities of computers, or that there is some special quality of the human mind that is necessary for thinking and yet cannot be duplicated by a machine. Arguments in favor of the basic premise must show that such a system is possible. The first step to answering the question is to clearly define intelligence. Intelligence Turing test. Alan Turing, in a famous and seminal 1950 paper, reduced the problem of defining intelligence to a simple question about conversation. He suggests that if a machine can answer any question put to it, using the same words that an ordinary person would, then we may call that machine intelligent. A modern version of his experimental design would use an online chat room, where one of the participants is a real person and one of the participants is a computer program. The program passes the test if no one can tell which of the two participants is human. Turing notes that no one ever asks the question, "Can people think?" He writes, instead of arguing continually over this point, it is usual to have a polite convention that everyone thinks. Turing's test extends this polite convention to machines. If a machine acts as intelligently as a human being, then it is as intelligent as a human being. One criticism of the Turing test is that it is explicitly anthropomorphic. If our ultimate goal is to create machines that are more intelligent than people, why should we insist that our machines must closely resemble people? Russell and Norvig write that aeronautical engineering texts do not define the goal of their field as making machines that fly so exactly like pigeons that they can fool other pigeons. Intelligent agent definition. Recent AI research defines intelligence in terms of intelligent agents. An agent is something which perceives and acts in an environment. A performance measure defines what counts as success for the agent. If an agent acts so as to maximize the expected value of a performance measure based on past experience and knowledge, then it is intelligent. Definitions like this one try to capture the essence of intelligence. They have the advantage that, unlike the Turing test, they do not also test for human traits that we may not want to consider intelligent, like the ability to be insulted or the temptation to lie. They have the disadvantage that they fail to make the common-sense differentiation between things that think and things that do not. By this definition, even a thermostat has a rudimentary intelligence and consciousness. Arguments that a machine can display general intelligence, the brain can be simulated. Hubert Dreyfus describes this argument as claiming that, if the nervous system obeys the laws of physics and chemistry, which we have every reason to suppose it does, then we ought to be able to reproduce the behavior of the nervous system with some physical device. This argument, first introduced as early as 1943 and vividly described by Hans Moravec in 1988, is now associated with futurist Ray Kurzweil, who estimates that computer power will be sufficient for a complete brain simulation by the year 2029. A non-real-time simulation of a thalamocortical model that has the size of the human brain was performed in 2005, and it took 50 days to simulate 1 second of brain dynamics on a cluster of 27 processors. Few disagree that a brain simulation is possible in theory, even critics of AI such as Hubert Dreyfus and John Searle. However, Searle points out that, in principle, anything can be simulated by a computer, thus bringing the definition to its breaking point leads to the conclusion that any process at all can technically be considered computation. What we wanted to know is what distinguishes the mind from thermostats and livers, he writes. Thus, merely mimicking the functioning of a brain would in itself be an admission of ignorance regarding intelligence and the nature of the mind. Human thinking is symbol processing. In 1963, Alan Newell and Herbert A. Simon proposed that symbol manipulation was the essence of both human and machine intelligence. They wrote, "A physical symbol system has the necessary and sufficient means of general intelligent action." This claim is very strong. It implies both that human thinking is a kind of symbol manipulation and that machines can be intelligent. Another version of this position was described by philosopher Hubert Dreyfus, who called it the psychological assumption. The mind can be viewed as a device operating on bits of information according to formal rules. A distinction is usually made between the kind of high-level symbols that directly correspond with objects in the world, such as less than dog greater than and less than tail greater than, and the more complex symbols that are present in a machine like a neural network. Early research into AI, called Good Old-Fashioned Artificial Intelligence by John Hougeland, focused on these kind of high-level symbols. Arguments against symbol processing. These arguments show that human thinking does not consist of high-level symbol manipulation. They do not show that artificial intelligence is impossible, only that a more than symbol processing is required. Lucas, Penrose and Gödel. In 1931, Kurt Gödel proved that it is always possible to create statements that a formal system could not prove. A human being, however, can see the truth of these Gödel statements. This led Gödel himself, the philosopher John Lucas and Roger Penrose to conclude that humans are not reducible to Turing machines. John Lucas wrote, "Gödel's theorem seems to me to prove that mechanism is false, that is, that minds cannot be explained as machines." Roger Penrose expanded on this argument in his 1989 book The Emperor's New Mind and his 1994 book, Shadows of the Mind. He presents a complex argument, and there are many details that need to be considered carefully. However, the essence of it is that it is impossible for a Turing machine to enumerate all possible Gödel sentences. Such a program will always have a Gödel sentence derivable from its program which it can never discover. Humans have no problem discovering these sentences and seeing the truth of them. So, therefore humans are not reducible to Turing machines. He also speculated that non-computable processes during collapse of quantum mechanical states gave humans this special advantage over machines. Normal quantum computers are only capable of reducing the complexity of Turing computable tasks and are still restricted to tasks within the scope of Turing machines. See quantum computer relation to computational complexity theory. By Penrose and Lucas's arguments, this is not sufficient, so he seeks for some other process involving new physics. For instance, quantum gravity, which might manifest new physics at the scale of the Planck mass via spontaneous quantum collapse of the wave function. These states, he suggested, occur both within neurons and also spanning more than one neuron. This was developed further into the ideas of orchestrated objective reduction. Counter-arguments to Lucas and Penrose. Many counter-arguments have been presented to both Lucas's and Penrose's theses. Douglas Hofstadter, in his Pulitzer Prize-winning book Gödel, Escher, Bach, An Eternal Golden Braid, explains that these Gödel statements always refer to the system itself, similar to the way the Epimenides paradox uses statements that refer to themselves, such as, "This statement is false," or "I am lying." But, of course, the Epimenides paradox applies to anything that makes statements, whether they are machines or humans, even Lucas himself. Consider. Lucas can't assert the truth of this statement. This statement is true but cannot be asserted by Lucas. This shows that Lucas himself is subject to the same limits that he describes for machines, as are all people, and so Lucas's argument is pointless. Hofstadter's book precedes Penrose's book, but a variation on the argument was brought up by Darrell McCulloch in Can Humans Escape Gödel?, where he uses a similar sentence. This sentence is not an unassailable belief of Roger Penrose. Roger Penrose's answer to this is to acknowledge that both humans and robots have such sentences when using informal language, but this is due to problems with formalizing natural language. To avoid such issues, his original argument was presented, for purposes of clarity, as an argument about p-sentences, sentences that are equivalent to a statement that such and such a Turing machine can never halt. These self-referring paradoxical sentences can't be put into that form. Russell and Norvig note that Gödel's argument only applies to what can theoretically be proved, given an infinite amount of memory and time. In practice, real machines have finite resources and will have difficulty proving many theorems. It is not necessary to prove everything in order to be intelligent. A different counter-argument is that Gödel's theorems do not apply to a given Turing machine both before and after it is given an input, where the necessary input is the interpretable description of the original trademark formal system. In other words, providing the required input is analogous to adding axioms and/or rules to the original TM's corresponding formal system. So, subsequent production of the original system's Gödel statement would no longer constitute a contradiction. Many other arguments have been put against his views. Some arguments raise technical points of detail in his logical deducations. Some are arguments against his suggestions for a biological basis for non-computable physics in quantum gravity. Some of the arguments attack the idea that the Gödel sentences can be seen to be true by humans. Perhaps we are limited in the same way that machines are, and only think we understand the notion of truth. In response to suggestions that humans take shortcuts to truth, and don't follow proper procedure and make mathematical mistakes, Roger Penrose acknowledges that this happens, and also that human mathematicians make mistakes. But he points out that we are able to correct our mistakes. His point, he says, is about what humans can do in principle. We have an underlying understanding of truth which we can rely on and use to find out mistakes. For references to some of the arguments, along with Penrose's counter-arguments against them, see Beyond the Doubting of a Shadow. Dreyfus. The primacy of unconscious skills. Hubert Dreyfus argued that human intelligence and expertise depended primarily on unconscious instincts rather than conscious symbolic manipulation, and argued that these unconscious skills would never be captured in formal rules. Dreyfus's argument had been anticipated by Turing in his 1950 paper Computing Machinery and Intelligence, where he had classified this as the argument from the informality of behavior. Turing argued in response that, just because we do not know the rules that govern a complex behavior, this does not mean that no such rules exist. He wrote, "We cannot so easily convince ourselves of the absence of complete laws of behavior. The only way we know of for finding such laws is scientific observation, and we certainly know of no circumstances under which we could say, we have searched enough. There are no such laws." Russell and Norvig point out that, in the years since Dreyfus published his critique, progress has been made towards discovering the rules that govern unconscious reasoning. The situated movement in robotics research attempts to capture our unconscious skills at perception and attention. Computational intelligence paradigms, such as neural nets, evolutionary algorithms and so on, are mostly directed at stimulated unconscious reasoning and learning. Statistical approaches to AI can make predictions which approach the accuracy of human intuitive guesses. Research into common sense knowledge has focused on reproducing the background or context of knowledge. In fact, AI research in general has moved away from high-level symbol manipulation or GOFAI, towards new models that are intended to capture more of our unconscious reasoning. Historian and AI researcher Daniel Crevier wrote that, "Time has proven the accuracy and perceptiveness of some of Dreyfus's comments.